Right, we're very happy to have Ben Chow tell us about visualizing Ricci-flat.
Thank you very much. I'd like to thank Wade and Elon for the invitation to speak in the members' colloquium. I'd like to thank Aaron for sponsoring my visit and IS for giving me the opportunity to visit this semester. Today I'll be talking about visualizing Hamilton's Ricci flow. And so the idea is that Riemannian geometry can be thought of as the most naive and simplest way to transfer Euclidean geometry, namely the notion of distance, length, and angle to a nonlinear setting. And so you can think of perhaps tangent spaces as linearizations of manifolds. And here we see visualizing the inner product. And then we just require that inner product very smoothly with the point. And then we have Riemannian geometry. And so on a smooth manifold, we can differentiate functions, but we can't, in general, differentiate in the natural way vector fields. So that changes when we're on a Riemannian manifold. And we have the Levi-Civita connection, which is a linear connection that's torsion-free and compatible with the metric. And from this, since we have a connection, we can define a curvature tensor. In this case, it's called the Riemann curvature tensor. And that's and from that, we can define sectional curvature associated to two planes in the tangent space. And if we take a line in the tangent space, then we can simply average over all two planes passing through that line to get the Ricci tensor. And this is a symmetric two tensor, just like the Riemannian metric is. And we can trace once more time and to get the scalar curvature, which is a function on the manifold. And so curvature determines how geodesics spread out. One of the basic facts is the route comparison term. So when we have positive curvature in this picture, geodesics tend to come together more than they do in Euclidean space. And the opposite is true in the case of negative curvature when the geodesics want to spread out more than Euclidean space. So the curvature sign influences the geometry of the manifold, namely in terms of behavior of geodesics. Okay, so we can think of the Ricci tensor as the Laplacian of the metric. And from that point of view, Hamilton's Ricci flow, which is the following, we have a one-parameter family of metrics, which will be denoted by G sub t, and its time derivative will be -2 times the Ricci tensor. So this makes sense because Ricci tensor is of the same type as the metric. And then you can start, say, with an initial metric G0 and try to flow. And here we have a picture of an initial metric on the far left that's kind of shaped like a double dumbbell. And then we can start with that metric, come up with a one-parameter family of metrics, and then have it satisfy this Ricci flow equation. And then something like this may happen. So the idea is when we have, the next right here in dimension 2, it'll start to expand and all that. And eventually the surface will shrink and become convex or have positive curvature. And it's not shown in this picture, but eventually it'll shrink to a round point. Okay, so there are a number of applications, most notably the proof by Hamilton Perelman of the Poincare conjecture, and something much more general, Thurston's imagization conjecture, and also more recently, there's a proof of the generalized Smale conjecture, namely in the case of spherical space forms by Bandler Kleiner using Ricci flow. And so Hatcher did the case of S3, Gabay did the case of hyperbolic manifolds earlier. And it can be proved, used to prove long-standing conjectures in geometry relating positive curvature, notably by Berman-Wilking and Bredlin-Shane. And they proved sphere theorems under some positive curvature assumption. Okay, so after 3 dimensions, the next case would be 4 manifolds. And in particular, there are a number of classical conjectures, maybe arguably 3 of the most well-known classical conjectures in smooth 4 manifold topology are the smooth Poincare conjecture, the smooth Schoenflies conjecture, and the Leibniz conjecture. And so then the question is, how might Ricci flow, what role might it play in 4 manifolds? It's incredibly complex, at least in the smooth case. In the topological case, it's much simpler, the behavior, at least certainly for simply connected manifolds. And so one can ask, can you geometrize 4 manifolds? This is implicit in the work of Bandler. And one answer could be that the Ricci flow decides what geometrization means. Okay, so I'll try to explain that in this talk a little bit, Bandler's program. So let's start with Einstein solutions. And so these will be, if we think of the space of metric and mod out by scaling, just multiplying by a positive constant, then these will be the fixed points of the flow. Okay, so we assume we have an Einstein metric here, and lambda could be a positive, 0, or negative, depending on the sign of the scaling curvature. And when lambda is positive, then we have positive scalar curvature. And in this case, the Ricci flow will not change its shape and just simply shrink it down to a point. If you start with a compact Einstein manifold with positive scalar curvature. And then on the other hand, if lambda is equal to 0, that means we have a Ricci-flat metric. Then this is actually a fixed point. We don't need to mod out by scaling. And it's a static solution to the Ricci flow. It exists for all time. And that's case 1. And already mentioned case 2. And the thing to note about that is that it's shrinking. So if you run the movie backwards, so if you think of Ricci flow as a movie, you run it backwards and it exists for all negative time. And that's called an ancient solution. And then on the flip side, we could have lambda negative, and then in this case, you can think of it as maybe starting from a point and then expanding further. Okay, so if we're in the category of closed orientable surfaces, you can think of lambda equals 0 as the case of a torus, like a flat torus, and lambda positive as two-sphere with constant curvature 1, say. And then the last case would be a surface of genus at least 2. Okay, so as a special case of Einstein manifolds, we have manifolds with constant sectional curvature. And if that's positive, they're called spherical space forms. And so here's just a picture of a spherical space form. I couldn't mod out by the root, so this is just an example, like perhaps S3. And under the Ricci flow, that will, so the Ricci curvature will be positive. The flow is ddt of G is negative 2 Ricci, so that will start shrinking. And that will shrink to a, we'll call it a round point in finite time. And one thing to notice is if we're in 3D, then Einstein manifolds are necessary space forms. So kind of the idea is that there's decomposition of the Riemann curvature tensor into its irreducible components. Because there's so many symmetries, the Weil tensor, which is totally trace B, must be equal to 0. And what that means is you can recover the full Riemann curvature tensor in terms of the Ricci tensor. And it turns out that from that formula, one deduces that being Einstein is equivalent to having constant sectional curvature. So that means in low dimensions, it's simplified. And the next solution we'll look at is a cylinder, and I'll just call it a generalized cylinder. So we could take a spherical space form of dimension k and take the product with the Euclidean space to get an solution to the Ricci flow. So the idea is the flat factor will not move, and then the spaceform direction will shrink. Okay, and so here I've just pictured a cylinder, and maybe you can think of that as S2 cross R. Now, the interesting thing is that it's not an Einstein metric, but you can think of it as a generalized Einstein metric. And you could frame it so that it satisfies the following equation that I've highlighted here. And so the idea is we can take a function just in the line direction right here and just make it like quadratic, normalized squared, actually kind of like a Gaussian. It's actually related to the heat kernel or conjugate heat kernel. But in any case, by defining F thus, we can write this equation, which is called the Ricci-Soliton equation. And so a generalized cylinder satisfies this. And so we'll kind of, I'll discuss that a little bit more. We'll come back to that. I went over that a bit quickly. So now we want to kind of look at what could possibly happen in general. So the first thing is, what if we restrict to have some type of positive curvature? And then this is the cases that Hamilton, Wilkin, and Brendan-Shane proved. So Hamilton did a case of positive Ricci curvature in dimension 3. He showed that if you start with something like that, then it shrinks to a point, asymptotically looking like a spherical space form. And then Perelman and Wilkin proved this under positive curvature operators, actually slightly weaker condition. And then Brendan-Shane proved the quarter pinching theorem that was open for many years. In fact, something stronger than that. Okay, so that's kind of a good case. So we kind of think of that's when, in a certain sense, the singularity is very frequent to a round point. So as Hamilton developed his theory, that was inspired by Yao, because Yao and Shane had looked at positive scalar curvature on 3 manifolds and often higher dimensions from the point of view of minimal hypersurfaces. So by looking at stable minimal hypersurfaces, basically they had a classification of the homotopy of 3 manifolds of positive scalar curvature, and this included connected sums. And so Yao suggested to Hamilton to look at the idea of Ricci flow, perhaps affecting the connected sum decomposition, at least in the category of positive scalar curvature metrics, in the hope that it might be approached to the Poincare conjecture. Okay, so here the idea is it's different than in 2 dimensions. So in 3 dimensions, we have a 2-sphere here, right here. And that has intrinsic curvature, so that's going to want to shrink. So if this was a 2-dimensional picture, then that circle would not want to shrink because it has no intrinsic curvature. And so what happens here is that the movie goes upward in time. So as t increases, you have a neck. If it's sufficiently pinched, then you'll keep pinching, and then you form a singularity. So when you have this pinch, there's actually like infinite curvature at the singularity time. But then one can hang microscopes on this and just try to expand more and more and look locally at this picture, and then you'll see a cylinder. Yes.
In all those pictures, you get a picture of the shape you have, but what happens to the coordinates? What is the, I don't, the homeomorphism in the original manifold and the one you obtain?
Well, this is intrinsic, so we're on a
Yes,
general. So this is coordinate. I mean, you could use local coordinates to calculate, but then this is all invariant. So it's completely independent of coordinates. I mean, you could ask if you have a point, like what happens to various points, but
no, you have still also homeomorphism between the original shape and the final shape, which will not respect the metric. So I was wondering what it will do.
Well, I mean, point-wise, you could, in a certain sense, you could just think of space-time as m cross 0t, half-open interval, and then you could just track a point, like x0 goes to xt, and just go like that, and just say what happens there. But kind of the modern way of thinking of it is that, due to Bamler, is that that's not really the world line. It should be governed by the conjugate heat kernel. So that conjugate heat kernel. So one couples the Ricci flow with the adjoint heat equation starting at a direct delta function. And then one, using the idea of variance and all that, tried to find out the moral center of that conjugate heat kernel. So Perelman used the reduced, he had a space-time geometry, and he had a notion of reduced distance. And that was, in some sense, very much tied to analysis, but is more, in a certain sense, more geometric. So Bamler's method is much more analytic or probabilistic. And then one can kind of make a better identification between that. I mean, the Ricci flow is diffeomorphism invariant and all that. And there are some questions about whether the diameter is bounded and all that actually were solved very recently. So the idea is when you kind of visualize that, you see a neck pinching. So this is a very stable case where you have round cylinders, but the idea is where it pinches, and if you go away from that and maybe even look at the singularity time where it's slightly before, and then what you must see is that the cylinder slowly grows in radius, very, very slowly, and all that, and it's just like will go that way. But what has to happen is basically the radius has to go from 0 to some finite number. So what does that mean? That means the radii of the spheres must slowly grow to an arbitrary large factor. And that looks like it would take forever, right? It's like it would happen on huge distance scales. But anything you have, you can simply shrink as much as you like. Yeah, but you could, everything you could just scale it and make it as small as you like. So if something looks huge, it could be scaled small. So you don't really know what the interaction with this heat equation is, non-linear heat equation. Yeah, I don't know if I answered your question, but the short answer is I don't know. I was just making up stuff.
In that example, you can just do a warped product, right? It stays exactly where it's supposed to be. Just take a sphere, do a warped product.
Yeah. I mean, that's, for example, the work of Angen and Knopf.
Looks like in that.
Yeah, so work in Angen and Knopf, they'll take a rotationally symmetric, and that way they can use barriers to actually show that this must happen and figure out their asymptotics. Okay, so what Hamilton envisioned was kind of a lopsided view of this, and he actually came up with the idea of a degenerate neck pinch. And so the idea is that instead of the dumbbell, you make one of the size smaller, right? And the idea is this might shrink at the same time this neck is shrinking like that. And then you might get a cusp singularity. Okay, so the idea is why should this happen? And one can just do the following, just take a dumbbell as an initial condition and then take a round sphere as another initial condition and just join the two by a one parameter family of initial conditions and say that there must be a transition point between two different singularity models. Namely, when you have a dumbbell, you get a cylinder singularity model. And then when you have a sphere, you get a sphere singularity model. And what we're going to see is something that interpolates between those two singularity models. But if you kind of dilate, so we're looking at it microscopically, and it depends on where you train the microscope. And if you do it along the neck, and then you'll just see what we saw before. So one of the associated singularity models is the cylinder, but that's not the only one. So on the other hand, we could kind of train microscopes at the tip of the singularity, and then one sees the Bryan soliton. So in the first case, we saw what was called the shrinking soliton, and this is called the steady soliton. There's nothing on the right-hand side, just zero. Okay, so this is a very key observation of Hamilton that such a singularity can form. And it's basically just kind of like a continuity argument. So think of this as perhaps having some properties of the cylinder and some properties of the sphere. It has positive curvature, but if you think about dimension reduction, because it's paraboloidal, the dimension reduces to a cylinder. So a model for that would be just saying that parabola dimension reduces to two straight lines.
Is the picture essentially independent of the dimension?
Yes. This is true in any dimension. So Bryan soliton and the degenerate neck pinch. So Bryan did it. You might have done it in 3 dimensions, and then I think maybe Tom Ivey, a student, did it in all dimensions, and then Gu and Zhu actually proved rigorously that this can happen. Okay, so this is just summarizing from the equational point of view, both the cylinder and the Bryan solitons, because we want to think about how these singularity models fit in the Ricci-flow analysis. Okay, so one key observation is that if we look at the Hessian of a function, we can think of it as the lead derivative of the metric with respect to the gradient of that function. So that means it's representing infinitesimal isometries of the metric. And so what that means is if you think of, if we could put a DDT in front of this and actually not have just a soliton structure, but a Ricci flow that's a soliton, and that's possible, then you get DDT of the metric is a lead derivative term plus scaling. But the lead derivative term is just from the effect of, trend moving by diffeomorphism. So that means that such a Ricci soliton is really a solution of Ricci flow that moves only by scaling up to isometry.
Oh, I forgot what F is.
F is a particular function that you show exists. So that's kind of the miraculous thing. It just comes out of nowhere, right? So so really the history of that is Hamilton, in the case of surfaces, has very specific F. That means it was a potential of the curvature. Laplacian of F is a scalar curvature minus the average. Okay, so scalar curvature minus the average has integral 0. So by Hodge's theory, there exists a function F whose Laplacian is R minus. But then Perelman actually coupled it with the conjugate, the heat kernel. So it was like U was a solution of the conjugate heat kernel, and then 4 pi tau to e to the minus, to the minus n over 2, e to the minus f was a solution of the conjugate heat kernel, and f was something like that. And then in the limit for the singularity models, one got this. Okay, but For here, we could just say that a soliton is simply a manifold, a metric, and a function that satisfies this equation. And the only question would be how would it arise in singularity analysis? But you can think of it just simply that way. And this is just kind of what I said earlier, that basically think of it, the static equation, maybe think of it in some sense as elliptic equation, how it corresponds to dynamically a solution to Ricci flow. It's simply moving by diffeomorphisms in the displayed equation. That's the PT covariates, and then scalings. Those are the positive constancies of T. Okay, so in this slide is simply the observation that when we look at the singularity analysis, the point of view is to look at sequences of points in time. So you don't necessarily want to fix a point and look at the time going to the singular time. You want to be more flexible than that. And one way to kind of see that's true is to think about the degenerate neck pinch. For certain sequences, we'll see a singular after dilation. Under a microscope, we see a cylinder, right? And then for other sequences of points and times, we'll see the blind soliton. Okay, so those are models, those are limits. And so those give you glimpses or reflect some aspect of the singularity formation of this degenerate neck pinch forming a cusp and all that. So, and so this is what you do. Really, the only comment is that what do we mean by convergence after rescaling? Then it's just more classically, it's just a pointed shear Gromov convergence. So Bandler will have F convergence, which is more general. Okay, so the takeaway from this slide is that a singularity model is such a limit under dilations, and you can think of it for simplicity as just shear Gromov pointed limits. So the shear Gromov pointed limit just simply means that up to diffeomorphism. Okay, so singularity models are kind of what we want to understand for singularity formation. That's kind of the first step, right? It's important to distinguish between the compact and the non-compact case. And so in the compact case, there's a very nice theorem of Johnson-Ley, and it says the following. If we have a Ricci flow on a closed manifold, and if you have a singularity model, so some sequence of dilations about points and times, and if that singularity model is compact, then, of course, from the shear Gromov convergence, it must be diffeomorphic to the original manifold, but the singularity model actually must admit a shrinking Ricci soliton structure. So what does that mean? Is think of it as a generalized Einstein metric with positive scalar curvature. So Ricci plus Hessian of F with some positive constant times the metric. There is some function for which it satisfies that equation, and you can just kind of make the hypothesis as maybe this is a good definition of canonical metric, and we'll think of, in this case, the manifold has been geometrized. Okay, so in a sense, we're just basically making the hypothesis that Ricci flow defines geometrization. Okay, it's maybe a little bit different in dimension 3, because in dimension 3, you have the sphere and tori or JSJ decompositions, right? And then Thurston's conjecture fit in with that, right? Posed that there are 8 geometries, homogeneous geometries, and then Hamilton's the point was Hamilton's Ricci flow and Perelman finally proving these theorems that they were made to kind of fit into that picture, the topological picture.
Is it clear they cannot be an oscillatory behavior?
That's what Perelman proved, that there could be no like closed orbit. So that's part of his, and follows from his entropy monotonicity formula. So they call them Wheeler solutions, or Ivy, I guess, call them Wheeler solutions, or well, it's standard terminology. Yeah. So that cannot happen. So that's one thing you would hope. Okay, so I'm now going to look at non-compact singularity models, and so let's look at Ricci-flat ALEs. And there's we can think of it this way. So we're looking at both shrinking and steady solitons. So steady soliton would be MGF, where Ricci plus Hessian of F equals 0. And then you can think about, well, what if F is just 0? Then it's Ricci-flat. And so the point is, Perelman's no local collapsing theorem says that if we have scalar curvature 0, and in particular, if it's Ricci-flat, then the manifold must have Euclidean volume growth, like in that sense. And then there's a wonderful theorem of Chiger and Neighbor that together with Bando, Kasua, and Nakajima says that just from having Ricci-flat and Euclidean volume growth, that it must be asymptotically locally Euclidean. Okay, so that's quite remarkable. And so the idea of asymptotically locally Euclidean is, if you think about it at infinity, then you find the right diffeomorphism. So it looks like to reasonably high order, the complement of a ball in R4 mod out by a subgroup of O4. Right? So it looks like some quotient. So globally, you can think of like maybe an orbifold quotient of R4 like that. And so there's like a 4 here, but it just had to be tau positive, and then Bando, Kasua, and Nakajima proved that could be upgraded from tau positive to tau equals 4. Okay, so what that means is that if we're interested in Ricci-flat metrics from the point of view of singularity analysis in Ricci flow in 4D, then you don't have to worry about the collapsing cases, or better said, kind of slower volume groups. You can really restrict to the ALE case, at least for finite time singularities. And so a well-known example is the Gucci-Hansen metric, which is on the cotangent bundle of S2. And this has a lot of symmetry, killing vector fields. It's also Hyper-Kähler. And the whole number reduces. And then there's actually a theorem of Appleton is that this particular Ricci-flat ALE, which is modeled on R for my Z2, can occur as a singularity model of Ricci flow. So then one can ask if any, I think this is unknown as far as I know, whether any Hyper-Kähler ALE form manifold can occur. Okay, so these spaces were classified by Kronhanger in the mid-80s.
Which metric on the cotangent bundle? The obvious one? No.
No, I mean, it's explicitly written down. It was written down by these physicists. It has various symmetries and all that in general. I don't think the metrics in general for the Hyper-Kähler metrics are explicitly written down, but they have a lot of nice properties analytically. Okay, so if we're thinking about 4-dimensional singularity models, of course, we want to think about 3-dimensional, right? Because we can just take a 3-manifold and cross it with a circle and run Ricci flow, and that would basically have the behavior of the 3D Ricci flow. And so there's a remarkable theorem, which is mainly due to the work of Hamilton, Perelman, and Brenla. And this is a classification of all possible orientable singularity models. And so what it says is that they actually have to be solitons. Okay, so this is a justification why one is interested in looking at solitons. So in particular, if it's a shrinking Ricci soliton, then it either must be a spherical spaceform or a cylinder or its Z2 quotient. Okay, so Z2 is just acting by antipodal map on S2 and a reflection on R. So it's orientation preserving. And then the other possibility is a steady soliton. In this case, it must be a Bryan soliton. The Bryan soliton, by the way, is rotationally symmetric. It's triboloidal, has linear curvature decay. Okay, so you could pose the question whether every 4D singularity model is either shrinking or steady Ricci soliton. Perhaps this is not the right question to ask, but I think it's still unknown. So in this talk, I do not want to talk too much about the details, so I think I'll speak a little bit about that in the talk next month in the analysis seminar. So people are interested in the curvature behavior, interested in volume growth, aspects of the geometry of infinity, and number of topological ends, for example. And so there's a book titled Ricci solitons and dimensions for higher with Brent Kochvar and Ovidio Montiano that discusses some of what's known about solitons in dimensions 4 and higher. Okay, so before we look in more detail, at least via pictures in 4D, we just note a few things about lower dimensions. In 2D, the only shrinking Ricci soliton, let's stick to orientable, and let's not include the Gaussian soliton on R2. Then it has to be the round S2. In 3D, the only compact singularity model is S3 mod gamma. Now, the other singularity models, is the splitting for S2 cross R, although it does have a Z2 quotient. And then we have the Bryant soliton. And as I mentioned before, dimension reduces to a cylinder. And then, of course, what you can do is simply take the 3D solitons and cross with R. And then one gets a shrinking soliton or steady soliton in those cases. And for the steady, like here, we'll just think of R as having potential function 0. And then when we look over here, we have to take that quadratic that I mentioned earlier. Okay, so then the question is what other 4D singularity models are possible? And so actually not very many are known. Okay, so let's first consider the non-compact 4D shrinking Ricci soliton. And so the first case is a huge departure from 3D. So in 3D, you cannot have asymptotic conical singularity formation, but this begins to occur in dimension 4. Okay, so there is a Kähler shrinking Ricci soliton on a line bundle over CP1, and this has degree -1, so it's diffeomorphic to C2 connected some CP2 bar, and this is basically U2 symmetric. And this is proven to exist by Perelman, Illman, and Knopf. It's asymptotically conical, and its asymptotic cone is a cone over a Berger sphere. Okay, and this type of singularity, this type of shrinking soliton can occur as a singularity model in 4D Ricci flow. Of course, S2 cross R2 is itself a shrinking Ricci soliton, and we can take a Z2 quotient. And then there's another shrinking soliton due to Bandler, Cifarelli, Conlin, and Durrell, and called the BCCD, Kähler shrinking Ricci soliton. And this is diffeomorphic to C cross CP1 blown up at one point. And maybe this is a little bit misleading, but say it's asymptotic to S2 cross R2. It's really asymptotic to S2 cross the cone over a circle, a radius between 0 and 1. But if you look at the infinity of that, then that will be S2 2 because the two-dimensional cone is flat. Now, you can think of those, maybe I call those like two cylinders, because the S2 is mentioned, call these three cylinders. And then, of course, we have this cylinder here, but so far there are no shrinking solitons asymptotic to that. So it might, it has geometry asymptotic to that, and then something else going on in the interior region. In fact, it's the state of art is much worse than that. It's not known for shrinking solitons whether how many ends they have, top-like ends. So you could just imagine one end looking like some geometry, another end looking like another geometry. Okay, so that was a couple of examples of shrinking solitons. Now let's look at steady solitons. In this case, there are a number here. As before, we mentioned the Ricci-flat ALEs, and the only ones known to exist are the Hyper-Kähler ones. And of course, there's a well-known conjecture that those are all. Besides that, there are ones with a lot of symmetry, so there are cohomogeneity 1, steady Ricci solitons. And these are on plane bundles over S2. With Euler class at least 3, and those were shown to exist by Appleton. Okay, so we can think of maybe the cake with one case as the rotation symmetric Riemann soliton. So the idea is these Appleton solitons will look like the Riemann solitons mod ZK, where K is at least 3, look like those asymptotically. And then you can take Z2 quotients of these Appleton solitons. So you get plane bundles over RP2. Okay, these are rather well-controlled geometries. So if you were to imagine a Ricci flow of surgery, that these would not cause problems. More of an issue is really our singularities modeled on everything in these lists that are in this page and the previous page. And the final thing I think I'll mention is Eli's flying wing type steady solitons. Okay, so it's a picture that it's not completely known the geometry of this. And so the idea is in the three-dimensional case, it'll actually look like a flying wing. So that means its asymptotic cone will be a two-dimensional wedge. But in this case, the asymptotic cone could be a ray. So it could grow slower, right, than linear. And then the idea is that it should look, as you go out infinity, as these kind of ovals, and so those ovals would be one dimension lower, so that'd be like a solution on S3, at least asymptotically, and it should be an ancient solution. So the idea is inside this four-dimensional steady Ricci soliton, you should see kind of Ricci flow in 3D asymptotically, and there is such a solution on S3 due to Perelman.
I did not understand the picture. What are the dimensions?
Okay, so this is four-dimensional.
Yes.
So there's a three-dimensional example, but let's think about a four-dimensional example, which might look like this. And then, so this right here would be a three-sphere. And then you can think of maybe a dimension reduces, right, to a three-dimensional solution across R, which case this will be Perelman's ancient solution. As you go off to infinity, these will look more and more like Bryan three-dimensional solitons like that. So that's kind of the rough geometry of that. Okay, so in the Hamilton Perelman theory, right, which just illustrates you can have, for example, finite extinction. For example, if you're on a homotopy 3 sphere, then you have to have that and all that. Then that's the first picture on the left. And then the middle is a degenerate neck pinch. And then you see a Bryan soliton as one of the singularity models. You also have the cylinder as another. And then in the final thing on the right, then you see just a neck pinch, and then you see a cylinder as the only singularity model. And this is just kind of like a space-time track or a movie, some still frames from a movie of Ricci flow. Here you can have like extinction of some components. Components can go on. Okay, so maybe we can think a little bit about the 4D cartoon picture, the Daimler's program. And so kind of a distinction is that spherical space forms can be embedded, right? So if we had a two-sided RP2 and a 3-manifold, it would be non-orientable. But we have many orientable S3 mod gammas cross, and we could cross R and just kind of think of the same picture we have in 3D, except this is a spherical space form, possibly with a non-trivial finite group gamma that you're quotienting out by. And then if you see a neck pinch, the idea is that the Ricci flow with surgery should do something like this. Okay, so we just cut out basically a finite cylinder part of that, and then attach just B4 mod gamma at 2 points. So what that would mean is that after surgery, you would have 2 orbifold points. Okay, so this is in one way, even if you're starting the smooth manifold category, you're forced into the orbifold category with isolated singularities. But these are smooth orbifolds. That means if you want to talk about functions or tensors on these orbifolds, there's a well-defined notion of smoothness, because if you're near this orbifold point, all you do is take the equivariant lift and just require that to be smooth. And so that notion of smoothness is defined even as, so you shouldn't think of it as a delta function curvature in infinity. You should think of it as actually just the other, from an analytical point of view, just as a smooth point with finite curvature. Something more complicated, but still a little bit idealized, is that what if we have a S2 cross R2 singularity model? Okay, and so now the point is, when you have a singularity model, there could be different versions of it. So at infinity, some core part of the Lie's steady soliton looks like S2 cross R2. Okay, so what that means is when you have singularity formation, you say S2 cross R2 is a singularity model, then there may be other associated singularity models for that singularity formation. So now we'll now just take a simple picture where S2 cross R2 is only singularity model associated to singularity formation. And so what you can kind of picture is a two-dimensional surface work product of S2 over that. And just imagine some of the S2s are much smaller, right? And the small ones, if you want Ricci flow, those will start to pinch. And maybe it's a very complicated set. Maybe it's even like a Cantor type set. But the point is, just like in 3D, so you could even have that in 3D. But how come you could do surgery? Well, the point is, topologically, this whole region of the manifold is very simple. And that's the point, even though analytically it could be very complicated. So the idea is it's reasonable to expect a surgery where here I removed some two balls cross S2, but those could be surfaces more generally. They could have topology there. And the idea is just you can cut that out and then try to glue in something in surgery. So there's a generalization of two surgeries you can do as follows. So this piece will be sigma 2, so it might not be connected. And then cross with S2, you remove that. And then just like a two surgery, you replace it by something which has the same boundary. So the boundary is S2 cross the boundary of sigma, and this will have the same boundary, and you glue that in. Okay, so the question is, can you do this reasonably in a geometric sense? And the answer is you should be able to. And the picture goes like this. And so this is the V3 cross boundary sigma 2. It's just boundary sigma 2 in this case is just two disjoint circles. And the V2 is just kind of like this thing right here. Okay, so in the case of sigma is just a two ball, this would be just a standard two surgery. And then what I described earlier with S3 mod gamma, gamma was equal to 1, that would have been a standard three surgery. But now what we're doing is the idea is Ricci flow is adding additional surgeries to this picture. And so this was used in 3D by Perelman to flow past singularities, and in particular necks and degenerate neck pinches. And the idea is that you can just simply take something that's asymptotic to a cylinder, round it off, and then show it has Ricci flow has some nice properties, etc. And the idea, this will have positive curvature, and you can use that to glue in. Okay, so why is that reasonable? So if you look at this picture, what you should do is just imagine the S2 radii being very, very small, right? So that means when you blow it up and you look at under a microscope, or not particularly high powered microscope perhaps, but you see this circle becomes flatter and flatter, right? So it looks more and more like a line. So what that means is the geometry approximates that of a product metric. So you can really imagine putting in Perelman's standard solution crossed with a line and actually affecting a surgery like this. So we'll just call that prophylactic two surgery. It's kind of preventing that things from happening. Okay, so if you had something like a Feldman, Illman, and Knopf singularity formation, basically there's a surgery that does a blowdown, like a smooth blowdown. So we'll just call that for Ricci flow flowdown. I think that's something, that terminology is due to Feldman, Illman, and Knopf. And so the idea is that you can imagine a Ricci flow where under a microscope, it's looking more like this FIK shrinker. And then near the singularity, it's starting at the singularity time. You see kind of zooming in at the singular point, you see the asymptotic cones over a Berger sphere. And then the idea is the resolution of that would be expanding solitons. So I haven't really mentioned much expanding solitons, right? But that was the flip side of shrinking. And then there's one on C2 that would resolve that and effect a smooth blowdown. Okay, so this, maybe we'll skip this slide, is basically what I was discussing on the previous slide. And then the idea is that the BCCD shrinking soliton would have a similar flowdown. And the idea is there we have CP1 across C blown up at one point, and then that would remove a connected CP2 subend. None of these happened in the spin case, right? Because spin is simply connected, it's equal to even intersection form, and the intersection for CP2 is just like 1. And then, so the idea is that similar surgeries would be possible for Appleton solitons. So the idea you can kind of think about, and this is not necessarily really necessary, but for Appleton soliton, you have curvature decaying linearly. So you have, you could imagine this picture, if you wanted to imagine this picture right before the singularity time, you could think about it this way, that you could just round this off toward infinity, and then the curvature, maximum curvature would drop by an arbitrary large factor. Right? If you chose to do that at the singularity time, then actually it reduces infinite curvature back to finite curvature. Okay, but the point is that you can maybe that's not necessary to do it this way, but you can just round it off in another way. And something similar should be true for Eli's flying wing singularity. And in this case, remember, we had a steady soliton, and this kind of looked like a brine, but it was kind of flattening out. Right? So these things look like Perelman's ancient solution, and these are getting more and more elongated, these S3s there. And, but in any case, maybe what you should kind of imagine is that you have a cusp, and that's going into some, right, then you have the finite curvature region. And if the finite curvature region is nice, then you should be able to do a surgery. So maybe a more precise way to think about that is that you'd have to have a canonical neighborhood term in the spirit of Perelman, namely that the high curvature regions of Ricci flow are epsilon close to singularity models and all that. But in any case, surgery in this case should also be possible. And in this case, there would be, if it's really like Eli's flying wing, there would be no topology change. Just like if you had a degenerate neck pinch, there's actually no topology change. So one thing I should remark is that in 3D Ricci flow, you have topological monotonicity, or monotonicity also means constant in every conceivable way, in a sense. But in 4D, it's very different. So the idea is in 4D, you could have like an embedded S2, say a trivial normal bundle. And then geometrically, you can make it look like a warp product, like what I showed on the previous slide. And then basically you could have that 2-knot shrinking down to a point. And then you would expect Ricci flow to affect the surgery on that 2-knot. And now 2 knots, a special case are spun 2 knots. And then the knot group associated 2 knot is isomorphic to the knot group of the 1 knot that's spun from. And so what that means is if you had, for example, a 2 knot in standard S4, that you could effect that 2 surgery on that 2 knot. And so Ricci flow on S4 would suddenly convert to a 4 manifold whose fundamental group was any 1 knot group. Okay, so certainly from the point of view of fundamental group, it's not, it could be very complicated, but the point is that for Leibniz's conjecture that signature is a cobordism invariant, and it's well known how you know, the second Betty number behaves under 2 and 3 surgeries. Okay, so maybe one can say this, you can interpret Daimler's work as pointing toward a geometrization conjecture for 4 manifolds. So there's going to be more surgery types And there's also kind of a long time picture where he has in the spirit of Hamilton Perelman, and of course others before them, notably Margulis, Thurston. There's this thick, thin decomposition. So the picture at infinity will kind of look like Einstein manifolds of negative scalar curvature and then collapsed pieces. And well, in 3D, the point is that 3D collapsed pieces are graph manifolds and hence Seifert-Fiber manifolds. But it presumably is a fair bit more complicated 4D, so one would have to develop kind of a theory of collapse for Ricci flow under certain geometric conditions of collapsing 4 manifolds. Okay, so one thing, so Bandler has a formula theory here, and one of the consequences is the following. If we do have singularity formation, and let's say our initial manifold's not diffeomorphic to a shrinking Ricci soliton. I mean, if it is, and if you're in the spin case, then, well, shrinking Ricci solitons have positive scalar curvature, and then you could just use the Lichnerowitz theorem to say the A hat genus is 0. The A hat genus is 1/8 the signature, so the signature would be 0. And certainly that would satisfy 11/8 that piece. So we're just going to look at when the manifold, the singularity model is non-compact. And then basically you have the 2 cylinders, the 3 cylinders, and Riemannian cones, where Riemannian cones either come from the flat overflow R4 mod gamma. Actually, in that case, it must come from a Ricci-flat ALE, if you have that. And then, oh, sorry, that's not true. That's only true in the steady case. So that's not true in general, but you either have that or asymptotically conical shrinking Ricci soliton. It's asymptotic cone. So you have these 3 possibilities. But that doesn't mean that the full picture of the singularity looks like that, right? Just like Eli's spline wing, you could see this as part of the singularity, but then it looks different, like for example, the Bryan soliton. Sorry. Okay, so this is just terminology. You can just call Ricci flow cobordism of flowboardism. It's going to be reflexive because you just flow little time, it won't change, and it's transitive, but it's not symmetric. Okay, so it would be amount to the question is what for the 11/8 conjecture, you want to show that the signature, there's not too much signature relative to the second Betty number, so you want this inequality. So if you had monotonicity, then that would certainly make it much easier, but that's not necessarily true. And that's I'm just speaking out to the time. And this is stuff that I've talked about already. Just get that. The takeaway from this slide is that even when you have ALE bubbling and you don't have the signature to a Betty number monotonicity, you can prove basically what's necessary, that if you end up with things that satisfy 11/8, then the original manifold does too. This is simply a comment about the Hitchin-Thorpe inequality. But in that case, the thin decomposition already discussed. And then, so the general question is, can Bandler's program prove we continue to be developed and eventually hope to prove the 11/8 conjecture, and more generally whether it can geometrize 4 manifolds. Generic Ricci flow, it's unclear whether such a notion would ever come in. Sorry for going over.
Thank you. Are there any questions?
Sorry, can you just tell us that 11/8 or 8/11 conjecture again?
Yeah,
I never.
I formulated-
Inequality go?
yeah, so it's not too much signature compared to Bennett. So for K3, so B2 would be 22, signature would be 16, so that would be the equality case. So the idea is like, right. So you can't have, I mean, it's written that way. Mike Friedman writes it that way, so, because it's more intuitive, like not too much.
Is there any weaker statement that's?
Well, yeah, that information, yeah, so it's proven like the tenates conjecture has been proven. And then Hopkins, Lin, Shi, and Shu have further improved through this result. So, but that's using homotopy theory.
There are no other questions? Let's thank Ben again.